anyone give me the definition of what is a chemical bond? Can you give me some thoughts about what might contribute to the definition of a chemical bond? What do we know? They bond together, agreed. What else? Good. It's two elements that are bonded together. What else?
Sharing of electrons.
Good. Okay, a sharing or even a trading of electrons. So there's two different types of bonds. We're going to look at both of those. Okay, so here's the definition of a bond. The attraction between the nuclei nuclei and valence electrons of different atoms. The attraction between the nuclei and valence electrons of different atoms. Now, when I say that phrase, valence electrons, is that ringing bells? Is it a term that we've heard before? What does valence electron mean? Are they the inside electrons or the outside electrons?
Inside.
Outside electrons. Valence electrons, let's write that in if we're not sure. Valence electrons are the outer shell electrons. Okay, and if you're not sure about this abbreviation right here, we should write it all the way out. Valence is VALENCE. Valence electrons, that's what that means. The outer shell electrons. That means that those are the electrons available for bonding. Okay, they are available to bond. Okay, so let's walk it back even a little bit more. Let's reach back into last semester when we talked about electron configurations, and we said that their outer electron is in the 2p orbital, right? If I said its outer electrons were in the 2p orbitals, that would mean that I'm somewhere in this row, right? And so that means that those valence electrons are anything in the second level. So if we were talking about carbon, for example, carbon is 2p2. Agreed? So carbon's electron configuration would look like this. 1s2, 2s2, 2p2. Are we in agreement with that for carbon? Its valence electrons would be the ones in the outer shell, right? These two and these two. So carbon would have a total of 4 valence electrons. They're full. That's an inner shell that's full, right? The 1s orbital is full with 2 electrons, and then we added another shell on top, right, when we come down to 2s. Okay? There's kind of a shortcut for us to know how many valence electrons there are. And we've talked about that too. But the shortcut for knowing how many valence electrons are in their shell go by their group number. So all of the elements in group 1 have 1 valence electron. All of the ones in group 2 have 2. You skip these guys. 3, 4, 5, 6, 7, and 8. You remember that rule? That our valence electron goes by their group number. So how many valence electrons would bromine have? Bromine is here. How many valence electrons would it have? 7. 7 valence electrons. All right, that's how many it would have. Available for bonding. That means for bromine, we don't care about any of the other electrons. We don't care about the ones that are inside. We only care about the outer shell electrons. Yeah. If there's an attraction between the nucleus and the valence electrons, what's the charge of the nucleus have to be? What's the charge of the nucleus? Like, tell me, what do we find in the nucleus? Are electrons found in the nucleus? Neutrons and protons. So what's the charge of the nucleus have to be? Positive. And the charge of the electrons has to be negative. So that's how they're attracted, right? The nucleus of one element and the electrons of the other come together. That's what causes that attraction and causes that bond to happen originally. Okay? So in order for them to be bonded, there has to be some sort of transaction that takes place. And when I say transaction, I mean there's got to be involvement of the electrons. Okay? And it can happen in 2 ways. So bonds can happen in 2 ways. So let's look at our types of bonds. The first is called an ionic bond. And we should know that word, right? Because we did ionic naming, right? And when we did ionic naming, that means it's between what? Metal and a nonmetal. So the same is true for an ionic bond. It's between a metal and a nonmetal. Okay, metal and nonmetal. And this is when atoms trade electrons. Trade is really important. Okay, they don't share electrons, they trade electrons. Okay, they don't share electrons, they trade electrons. And so I want to give us kind of an example of this. I want to show a really simple but clear example of an ionic bond. Okay, let's see what happens in an ionic bond at the main level, okay? So if I'm going to give an example of an ionic bond, I'm going to use a really simple compound, and I'm going to use sodium chloride. Sodium chloride is Na and Cl, right? Can you tell me how many valence electrons does sodium have?
One.
Yeah, it's in group 1 right here, so it has 1 valence electron. So here is sodium's electron. I'm just going to put it right beside it. And I'm going to draw chlorine in a different color so we have a better idea. Okay, chlorine, how many valence electrons does chlorine have? 7. So let's draw them. 1, 2, 3, 4, 5, 6, and 7. That's kind of the notation that we draw these electrons in, is that we try to keep them in pairs. Right? We draw 2, 2, 2, and then I've got my 7th electron there. Okay, so here's how sodium and chloride begin, right? That's how they start. They hang out. They're neutral at this point. But if a bond is going to take place, in particular an ionic bond is going to take place, there has to be a trading of electrons, okay? Or I should maybe even say a give or a take. Okay, we're not necessarily going to trade. We're going to give and take. So let me ask a different question here. Do you know how many electrons does an atom want in its shell, its outermost shell? How many does it want? Say it. 8. It wants its S and its P shells to be full. And S can hold 2 and P can hold 6. So it wants those to be full, which combined would be 8. Do we agree with that? So 8 is our magic number. We want to what we call the octet rule. We want to complete the octet rule. So let's think about this. If we want 8 electrons, what's the easiest thing that could happen here?
Add 1 to chlorine.
Okay, but where could that 1 electron come from? It could come from sodium. Sodium's going to give its electron away. Because when it does that, now sodium's outer electron is gone, which leaves it with now a new outer shell that is already full. Right? Do you see what I'm saying? We peeled away that outer layer, and whatever was underneath that was already full. So when sodium did that, it gave its electron to chlorine. What kind of charge did that leave sodium with?
Plus.
A plus charge, right? It gave away its electron. So now it's short an electron, which means sodium has a +1 charge. And if chlorine took on an extra electron, what is its charge? -1. And what happens when a positive and negative are by each other? Well, they do end up canceling for a whole molecule, but they attract, right? It's like opposite ends of a magnet, right? They attract. So when we have a positive and a negative charge like that, they're going to attract, and this is what we consider an ionic bond, okay? They both now have formal charges that bring them together, and so they are what's called an ionic bond, okay? So there was a give and take of electron there, right? Sodium gave theirs away, chlorine took it in, which resulted in them each having a charge, and now they hang out really close to each other and call it a bond. Right? That's what's happening. There's no sharing happening there, but we have the result of this net charge that causes them to want to hang out really close, right? Which is called a bond. Does that kind of make sense? So ionic bonds are kind of simplistic in that way, and it's unfortunate it's not the one that we work with a whole lot, but I want you to see the picture of that. Okay, do we have any questions of how that works? Okay. Let's look now at the second type of main bond called a covalent bond. And we already did covalent naming. So what do we know the molecules that are covalent are between what? two nonmetals. So this is two nonmetals. This is going to be what we work with the most in this chapter, is really looking at covalent bonds and how they work. Because in a covalent bond, you can't do a positive minus attraction, right? Because covalents are all negatively charged. So nonmetals are all negatively charged. So we're not going to see that plus minus attraction. What we are going to see in a covalent bond is the sharing of electrons. Okay, and that's really important. So sharing of electrons, I want us to understand that for covalent bonds is that we're going to share electrons. Okay. Although we gave two categories of bonds, okay, the first which is ionic, and the opposite side of the spectrum is covalent, right? Here in ionic bonds, they completely give away electrons, right? But down in covalent bonds, they share electrons. But the reality is that all atomic bonds fall somewhere on like a spectrum here. Okay, do you know what I mean when I say spectrum? Right? Bonds fall somewhere between perfectly ionic and perfectly covalent. Okay, they might be sharing electrons. Let's give an example here. Let's say that I have a bond. Let's say that I have a bond between oxygen and hydrogen. And we looked at our previous, our example at the very beginning, and we said they're each going to contribute an electron, and it's bonded. But what happens if this bond is not even? Like, what if oxygen is hogging the electrons? It might look something like this. Let's just draw our bond there for fun. But both of our electrons are pulled towards oxygen's side, right? That falls somewhere closer to an ionic bond, right? Do you see what I'm saying? We can have bonds that are perfectly covalent, where they share the electrons perfectly evenly, or we can have such uneven sharing of electrons that now it's just a give and take, which is an ionic bond. So chemical bonds fall on a spectrum, somewhere between ionic and covalent. Okay, we'll kind of talk about that more as we get through our process here, but it's not necessarily that it's 100% an ionic bond or 100% a covalent bond. It's all about how the electrons are shared. And we start with like an even tug of war, right? An even sharing, and then eventually someone hogs the electron so much that they just like straight take it. That's what happened in chlorine's case, right? Chlorine just took the electron away. And so now it's not sharing at all, right? It's a give and a take. Does that kind of make sense how that can work? It's kind of a sliding scale of where those fall. And it just depends on basically how strong the atom is, right? I want you to think about it like a tug of war. If we have two atoms that are the same type, like let's say, for example, we had oxygen bonded to another oxygen. What's the prediction for that bond? Do you think they're sharing it evenly or unevenly? Yeah, they're sharing it evenly, right? Both of those oxygens have equal strength. So they're pulling on electrons with equal strength, which would mean that type of a bond would be perfectly covalent, right? Because if you're thinking about it as a tug of war, they both have equal strength. Okay? All right, very good. So let's take a look at this example right here. If we have electrons that are sharing, but they are not sharing evenly, do we know the name for that? Has anyone heard that term before? That is called a polar bond. Okay, I want you to write that down. That's called a polar bond. So a polar bond is when we have uneven sharing of electrons, right? It's within a bond, we are sharing electrons unevenly. Okay, one of our atoms wants the electrons more than the other. Okay, one of the atoms wants the electrons more than the other. Okay, so that is called a polar bond. Okay. A non-polar covalent bond would be even sharing of electrons. So that would be an example of the very last one we gave where they're both oxygen, right? And they're pulling on it with equal strength. That would be considered a non-polar covalent bond, right? When we say non-polar, we think of like nice and symmetrical and even and all of those things, okay? And polar means we've got opposites, right? We've got one end of our spectrum that is different than the other. All right, so I want to kind of give us an introduction there to polarity, but we're not going to dive deeper there just yet. But I want us to understand that if we've got a bond that is polar, our electrons are just being pulled one way, right? They're kind of being pulled one way or the other. So that's a good visual for us to think about. If it's polar, our electrons are kind of being hogged by one of our atoms, okay? So let's get to now our structures that we were talking about. How can we start to represent these electrons and these bonds in molecules, right? How can we do that? So let's dive a little bit deeper into covalent bonding here. Okay, we're going to dive deeper into covalent bonding. So that's where they share electrons. And how many electrons did we say that atoms want to be happy, to be complete? What's their goal? Okay, so each atom wants 8 electrons. We call that the octet rule. That's really important. Oops. Octet rule. Okay, highlight that. Circle it, whatever you need to. The octet rule is really important. You're going to hear me say it a lot, right? We want to complete the octet rule, which means that atoms can count 8 electrons near them, okay? And that includes electrons that are their own and the electrons that are shared, okay? So theirs and shared electrons get counted in their octet, okay? Let's start with an example here. I want to look at a molecule of 2 fluorine atoms bonded to one another. So I want you to draw out a fluorine atom, one fluorine atom next to another, and let's put their electrons on, okay? How many valence electrons does each fluorine atom have? 7, right? Because it's in group 7 right over there. So it's going to have 7. And we said when we start to draw atoms like this, we're going to think of the atoms as having 4 sides. 1, 2, 3, 4. Okay? And we're going to draw our electrons in pairs if we can. So we're going to put 2, 4, 6, and one guy's left out here, 7. The other fluorine atom will look identical, won't it? Okay, I'm going to put it in a different color so we can see. But here's my next fluorine atom, 2, 4, 6, and 7. Okay, so if these two fluorine atoms need to bond, would an ionic bond work here? Would it work for this to go over here? Not really, because then it leaves this as an incomplete, right? If that happens, now we're left with only 6 electrons for that red fluorine. And the purple fluorine has 8, but the red one's not happy, right? We want them both to be able to experience the octet. So now we have to look at what would it look like to have a covalent bond. And a covalent bond means that they share those electrons. Okay, thinking back to our very first example we looked at this morning, how do we represent a covalent bond? With a line. We draw a line. So what we're going to do is connect these two right here, and we're going to count that as a bond. And so when we do that, now we can look and see, is our octet fulfilled? So if I look at this red fluorine right here, here's 2 electrons, 4, 6, and then it gets to count both of these electrons as its own. because they're sharing them now. So does this red fluorine have its octet fulfilled? Yeah, 2, 4, 6, and 8 within that bond. And then if we look at the purple one, it has 2, 4, 6. It also gets to count those as its shared electrons. So now both fluorines have a complete and filled octet, which means this is a complete structure, right? This is a happy molecule. Okay. When we start getting better at drawing our molecules, we will just make our bond just the line itself. We don't have to draw the electrons at all, right? We'll just draw the line. Does that make sense? Okay, that's all we'll have to do there. And we know that the bond, when we draw it, contains 2 electrons, 1 from each atom. Okay? What did we say these dots represent? They still represent electrons, but are these electrons bonded to anything? No. These are called, all of these right here, these outer electrons are called a lone pair. It's a lone pair. That means it's not bonded, and it's a pair, right? A pair means how many? 2, right? It is a lone pair. So when we say how many lone pairs does this fluorine have? Well, this one has 1, 2, 3 lone pairs. Pairs of things that are not bonded. Okay, so it is a pair of electrons. So there's 3 lone pairs on that one. This line is a covalent bond. Now, if you had to take a guess, is that going to be a polar covalent bond or a non-polar covalent bond? Non-polar. Because we know because it's the same, 2 of the same element. 2 of the same element tells us it's non-polar. All right, there's one other thing that I want us to check as we're working through our structures and as we're starting to build these structures. There's one other thing that we can do to check our work to make sure we're doing them correctly, and that's to check the total number of electrons in the structure. So I want us to count the total number of electrons represented, not like the shared, but the total number. So we have 2, 4, 6, 8 electrons plus 2 more is 10, 12. We have 14 electrons present, don't we? Okay, I'm sorry. We are going to count them. We're just not going to count them twice. Like when we were counting octet, we got to count this one for the red and for the purple. But when we count total electrons, we're just counting them once. Does that make sense? So in total, we have 2, 4, 6, 8, 10, 12, 14 electrons present. Okay, we have 14 electrons in our structure. And how many did we say each fluorine brought to the table?
7.
They each brought 7, right? So that means that we have the correct number of valence electrons. Our total electrons in our structure should always add up to the sum of our valence electrons. Okay, that'll usually really be our first step, actually, to tell us how many electrons we need. That's right. That's right. Okay, are we ready to try some? I'm gonna give us some steps, some guiding steps to be able to draw our structures. Okay? So let's spread out our rules for Lewis structures. Okay? This bond that we just drew, or this diagram we just draw, is called a Lewis structure. Okay, and so here's our rules for Lewis structure, or our steps, or however you want to say. Right? I'm going to give you some guiding steps here. The first thing that we're actually going to do when we go to draw our Lewis structures is the last thing we did here, and that's actually going to be to count the valence electrons. So the very first thing we want to do is find out how many valence electrons should there be in my structure. So if I have this example, if I want to draw the Lewis structure for NH3, okay, so let's show an example. If I wanted to start to draw the Lewis structure for NH3, I would count how many valence electrons are in nitrogen. I'd go look on the periodic table and find out it's in group 5. So there would be 5. Plus, each hydrogen has how many valence electrons? They each have 1, so that's 3, which means I would need a total of 8 electrons in my structure somewhere, in my diagram. Does that kind of make sense? That's the very first thing we're going to do is count our electrons to find out how many will we need to have in our structure. Okay, that's step 1. Step 2 is to build what I call the skeleton. Build the skeleton. And what that means is that we're going to lay out the elements, but we're not going to start putting on any electrons yet. We're just going to draw out the elements themselves. Okay? And so how do we know what our skeleton looks like? I'm going to give you a couple nudges here. If we have carbon, carbon goes in the middle. Okay, so if you ever have carbon, it needs to go in the middle of the atom, right? So as we build our skeleton and we have carbon, let me give you an example here. If we had CCl4 and we were trying to draw that structure, my Lewis structure would start like this: carbon in the middle and then a Cl on each side, because I would need to have 4 of those Cl atoms. Does that kind of make sense? That right there is the skeleton. I don't draw any electrons yet. I just put in the elements by themselves. You see what I mean there? You know why I call it the skeleton? It's just like the base thing, right? It's what we're going to build all the other stuff from. Okay, so we're going to count our electrons and then build our skeleton. Okay, if carbon is not in the molecule, so if there's no carbon there, the element that is listed first will go in the middle. Okay, the element that's listed first would go in the middle. And then we just spread the outer atoms, evenly around the outside. Okay? The last little nudge I'll give you on this rule is that hydrogen never, ever goes in the middle. Okay? And the middle atom I call the central atom, because what's central mean? It means middle, right? Middle. So when we say the central atom, hydrogen is never going to get to be the central atom. Can you give me some thoughts as to why hydrogen's never the central atom?
Because it only has one.
It only has one electron, right? It's only available to bond with one thing. So it never gets more than that. It only ever gets a single bond, and that's it. Okay, so hydrogen never gets to go in the middle. All right, step 3, after we've built our skeleton, is to bond the central atom to each outer atom and fill in electrons to complete the octet. Now that step is kind of loaded, right? Because that can be a little bit tricky to do, but that's the goal. Is that we want to bond the central atom to each outer one, and then we start to fill in our electrons to complete our octets. Okay. So those are the 3 steps, right? And the 3 steps seem simple, but sometimes our Lewis structures can get a little bit complex, and we're going to work through that, okay? But we're going to try to start with ones that really follow the rules, and then as we get really good at them, we'll see that there are some that are exceptions to the rule, right? That they can do different things. Yeah. You may. All right, are we ready to start one? First of all, could we name the molecule? Is it ionic or covalent? It's covalent. So we're going to call it silicon tetrahydride. Good. Tetrahydride. That's a tough one. Silicon tetrahydride. Okay. So the first thing that we're going to do is count our electrons. So silicon gives us how many? 4. Good. And we have 4 hydrogens that each give us 1 electron each. So 1 electron times 4, which means I need a total of 8 electrons in my structure. Okay, I'm going to need 8 electrons in my structure. So that gives me an idea. My next step is to build my skeleton. So which element needs to go in the middle of my skeleton here? Has to be silicon. Why can't it be hydrogen? There's only 1 electron per hydrogen, right? And there's 4 hydrogens. How could they go in the middle and be bond? Like, that doesn't make sense, right? Silicon is the obvious choice. So we're going to put silicon in the middle, Si, and then we're going to put a hydrogen on each side. Remember, for right now, we kind of act like our elements have 4 sides, right? A box around them. So there's my skeleton. Simple enough, right? My next and third step is to bond the central atom to each of the outer atoms, right? And I don't need to bother drawing the individual electrons and then drawing the bond. I can if I want, but I don't have to. I can just draw the bond knowing that there is an electron present from each of those atoms. Does that make sense? You don't have to draw out the individual electrons. You can just draw the bond. Because I know that each atom has contributed an electron to that bond. So, if I do that, I've got all my bonds have been made. How many electrons did I use by making up all those bonds? I used 8, right? Because there's 2 electrons per bond. So 2, 4, 6, and 8. And is that all the electrons I'm allowed to use? It is. So that means I can't add anything else. And so now I'm to the point where I just have to check, right? Is my octet complete? Is it not, right? I'm going to look at each of my atoms and say, okay, for my central atom silicon, I get to count the shared electrons when I'm looking at the octet. So 2, 4, 6, 8. So is silicon happy? Okay. Now what about hydrogen? Does it need a complete octet? It's one of the ones that doesn't. Hydrogen and helium don't need a complete octet because they're in the very first shell. So hydrogen is perfectly happy with just single bonds. So this is a good and complete Lewis structure. So that's our final answer right there. Right? We used up all of our electrons, no extra, we're not short, and we've got a complete octet. Okay? We feeling okay about that simple one? Okay, let's try another one here. Let's try NH3. NH3. Okay. We already actually counted our valence electrons here earlier in our first step when we were practicing, but nitrogen gives us 5, plus the 3 from hydrogen means I need 8 electrons in my structure. I have to have 8 electrons in my structure. What's my skeleton going to look like? Nitrogen in the middle. And then we're just going to spread the hydrogens out kind of like a triangle, right? We want to get them as far apart from each other as we can. That's the goal, is that our atoms want to be oriented as far apart from each other as they can be. So that's the step 2, building the skeleton. Now I'm going to bond. And when I do that, I use up 2, 4, 6 electrons, didn't I? By making those bonds, I used up 6, which means I have 2 electrons left I need to put on my structure somewhere. All right, I can't leave them off. They have to be on there. So now I need to look and say, is there an element that's unhappy? Is there an element that does not have a complete octet? Which one is it? Nitrogen. And it right now, how many does it have?
6.
Yep, it has 2, 4, 6. And so I need to put these last 2 electrons on nitrogen. Now, can I put them like this, 1 and 2? Or how did we say they need to exist as? A pair, right? We need to put them on as a lone pair. So that means I can put them, where I put them doesn't matter. I just need to put them together. So it can be a pair that looks just like that, right? Or I could have put my pair right here, right? Or I could have put my pair right here. It doesn't really make a difference. No, we don't want to put them right here because that kind of symbolizes that it's on the bond. Like 1 there. Nope. We want them to look like a pair. So it doesn't matter what gap you put them in, just put them in a gap and put them together. right? Keep them as a pair there. So now I can double check, right? I've used 2, 4, 6, 8 electrons total, which is what I wanted. And nitrogen is happy. And is hydrogen happy?
Yes.
Because it just went single bond, so it's good to go. All right, let's try PF3. PF3, can we name it? Phosphorus. Trifluoride. Phosphorus trifluoride. Maybe you guys said that and I just missed it, but phosphorus trifluoride, because it is a covalent, we want to make sure we include that prefix.
6.
Phosphorus trifluoride. All right, so phosphorus gives us how many? 5. Because it's in the 5th row, so we just count. 1, 2, 3, 4, 5. So it's in group 5, that's how we know. Yep.
It's always going to equal 8.
Okay, good question. No, it won't always equal 8. It should. This number of electrons should always be even. That's a very good clue for us. It should always be even, but it won't always be 8 or even a multiple of 8. Okay? Because let's see what this one comes out to be. When we put in 3 fluorines, how many electrons do those fluorines give us?
21.
Yeah, they each give us 7, and there's 3 of them. So that means 3 times 7 is 21, plus 5 is 26 electrons need to be present. That's not a multiple of 8, right? Which is okay. But it is even, and that's a must. So that number should always come out even. So if it doesn't, that's a red flag. Okay?
That's a red flag.
No, because it's even. So we're fine. All right, let's build the skeleton. Let's build the skeleton. What's going to go in the middle? Not potassium, but it is the P. Phosphorus, yeah. Okay, so phosphorus goes in the middle. Fluorine, fluorine, fluorine. It looks a lot like our last skeleton, doesn't it? Right? So now our goal is to put our electrons in. So we're going to go 2, 4, and 6. So out of our 26 electrons, we've used 6. We have 20 electrons left to put on. And right now, none of our elements are happy because fluorine does need a complete octet. Phosphorus does need a complete octet. So here's the process now. After you've bonded your atoms to the outer atoms, you're going to go fill your octets outward first and then inward. So we're going to fill the outer ones first, then come in. So I'm going to start on this fluorine and add 3 lone pairs because that gets this fluorine to be a full octet. Would we agree? 2, 4, 6, and 8. Okay. I'll do the same thing on the other fluorine. 2, 4, 6, and that's a complete octet. 2, 4, and 6. So I've used up 18 more electrons. I have 2 left.
You can just connect them on this side like you did in
Like this?
No. Like the 2 dots. You can go 2 dots.
I put, that's okay. Nope, that's exactly right. We've got 2 electrons left, and phosphorus I know needs them because it does not have a full octet yet. So I'm just going to drop them in a gap somewhere. Work. C2H4. C will go in the middle. Very good. Let's, yes. Let's count our electrons for this one. Okay. Each carbon gives us how many? 4. And there's 2 of them. And each hydrogen gives us 1, and there's 4 of them. So 8 plus 4 is 12 electrons. So did our number come out even?
Yes.
That's what we want. It has to come out even. Okay. Carbon has to go in the middle, but how many carbons do we have? 2. Okay, so we essentially basically here are going to have 2 central atoms. So we're going to draw them just like this, right next to each other, carbon and carbon. Okay, we've got 2 of them in the center. And then the 4 hydrogen need to be split around evenly, right? Those 2 carbons are sharing those 4 hydrogen. Does that kind of make sense how we draw that skeleton? And they could be straight up and down. They don't have to be at an angle, right? That part of it is not that big of a deal, but we need to make sure that each carbon has 2 hydrogens on it. Okay, so let's start looking at our electrons now. I'm going to have to bond everything. So I need to bond carbon to carbon, carbon to hydrogen, 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 hydrogen. Now, here's what we won't do. We won't take this one and bond it. Why won't that work?
That just cannot work.
Agreed.
It's already connected.
Okay, almost. But it's hydrogen only has one. Hydrogen cannot have more than one bond. So we can't do that. We can't bond hydrogen to hydrogen, right? And that's not going to work. We can't bond hydrogen, right? None of that will work because hydrogen is only allowed a single bond. That's it. So let's see what we need. We've used how many? 2, 4, 6, 8, 10. We've used 10. So that means we have 2 electrons left. Oh, this is bothering me. Okay. 2 electrons left. So like we said, what can we just do this?
Would we put 1 electron on each carbon?
Okay, good question. Tell me why this doesn't work first. Because our other carbon still sad, right? It doesn't have a complete octet. Right now, this carbon only has 2, 4, 6.
Can you make 2 lines?
Yeah. Okay, so let me go back to Ava's question one time. Can you do an electron on each one? What do we think about that?
Oh, I wouldn't make an octet.
Okay, it wouldn't make an octet, and they have to exist as a pair.
Would you connect them then? Those 2 electrons?
Yeah, okay, good. So that's what we're going to look at, is you're going to take these 2 electrons that you have right here and just move them into a bond. Okay, which is the same visually as saying they each have an electron here and we bond them, right? But we're going to move those 2 electrons into a bond. That way they can share them and each count them as their own. So if you're going through your structure and you feel like you don't have enough electrons, like I need more electrons, you might have to use a double bond, which is what this is called, double bond. Okay, that's called a double bond. So if I go to count, let's do our full count here. We should have had a total of 12 electrons. 2, 4, 6, 8, 10, 12 electrons. So that's good. And then this carbon's octet, 2, 4, 6, 8, all good. 2, 4, 6, 8, all good. Right? Because the shared ones get to be counted as the octet for each of those atoms.